Yeah, thank you very much for the introduction. I would also like to thank everyone for coming here. It's always a great pleasure to be at IPAM. And yeah, so I would like to talk about deep learning and modeling, taking the best out of both worlds. And since this is a workshop focused on medical imaging, the application I would like to show you then in the second part of my talk is computed tomography, in particular limited angle computed tomography. And I would like to show you two approaches towards this problem, which both pursue this strategy, namely driving the model-based approach as far as possible and using the deep learning only, let's say, for what the model-based approach cannot cope with. But let me start with a bit broader perspective. So I think we are living in an exciting time. I mean, the 21st century, most of the technological advances are based on a rigorous mathematical modeling, simulation, optimization approach. Design of airplane wings, and so on. But then at the same time, we observe, and I think this is also why we are here, that for certain applications, these methods reach a limit. So for instance, if you would like to do, say, atomistic molecular dynamics, then you see that there are very rare events which happen at ultra-long time scales. And so if you really drive a canonical mathematical modeling approach, you will never capture those events. And I mean, here as an example for this workshop, medical imaging, if you have very distorted data sets, if you have maybe highly underdetermined measurements, you have huge chunks of data which are missing, then model-based approaches will not pursue. So there's a pressing need to go beyond this, let's say, pure modeling, simulation, optimization world. On the other hand, we have the world of artificial intelligence, deep learning, which, and there was, in the last talk also the question, do we think that deep learning will change the world completely? We see that there are certain instances where, there's a huge impact already also, for instance, pre-screening job applications. So these are methods which impact everyone, and in particular in healthcare, and this is the topic here of this workshop. But at the same time, we are also aware of the problem, and this was also already discussed in several talks, that there are just very few theoretical results explaining their success. And also, for instance, concerning robustness and so on, particularly in medical imaging, this is a tremendous problem. The current trend which we observe is that often these pure data-driven approaches are not and do not perform best, but what performs best is, in some sense, to take an optimal balancing between the data-driven and model-based approaches. And there are various ways you can drive this. So you can have machine learning with physical constraints. You can set up, for instance, the parametric PDEs, where you learn the parameters from the data set. Data assimilation also goes in that direction. Or also, you just drive a simulation based on a partial differential equation, and then the simulated data you then afterwards analyze with deep learning techniques. And so this will be the theme also of this talk. I would like to show you, as I said, two approaches where we actually pursue exactly this strategy. So let me start with an outline of my talk. We first need to discuss or review a couple of things from inverse problems. The typical model-based approach I would like to use in this talk is sparse regularization. For inverse problems, we will not deal with wavelets here, but with a bit different system, maybe an improved system, Shearlet systems. And also we will take a particular viewpoint later on towards solving the problem. Because what you see is if you, let's say, do recovery, for instance, in computed tomography, then what is of key importance is to recover edge structures. Because, these are also very much adapted to the human visual system, because the human visual system reacts very strongly to edge structures, curvilinear structures. And so this can be phrased in terms of a particular framework called microlocal analysis. It relates to wavefront sets. And so this will be also then the guiding principle which we use setting up our approaches. And so, don't worry if you don't know anything about it. I will explain everything in a very high-level viewpoint. Then I would like to briefly review deep neural networks and inverse problems, maybe a bit also mathematical viewpoint, and then come to our approaches concerning computed tomography, in particular limited angle computed tomography. What I would like to show you are actually conceptual approaches which you could also use for other problem settings, but here I would like to focus on this. And the two approaches are ones which we call learning the invisible, which is more related to the limited angle computed tomography. And then this is based on extracting edges and using these for regularization. Okay, so that's the program. So let's start with reviewing some instances of inverse problems and then also introducing these systems, which we'll use also in our algorithmic approaches. Yeah, I think we saw it already in several talks. Generalization of Tikhonov regularization is a very popular way to solve inverse problems. If we have an inverse problem, we solve it by minimizing this functional, and the key question certainly is how to choose this penalty term or this regularization term. There's a whole zoo of different approaches we can pursue. It is designed to ensure continuous dependence on the data, but also mostly to incorporate some properties of the solution. And depending on the problem, certainly you have numerous different, let's say, settings, and therefore also numerous different regularization terms one could use. Now here we would like to take a sparsity viewpoint because, and this is also now a common paradigm, the world is compressible, so typically for every data set we can find a representation system which sparsifies our data. The most popular is the Wavefront transform, which already appeared in several talks. So I think I don't need to review it in detail. A Wavefront system has, the elements have this shape, so you have a scaling factor, you have a translation factor, and then the Wavefront transform is taking an image, for instance, computing the Wavefront decomposition, which looks like this, and what you see here is that many of those parts are black. These are zeros, so this is also where JPEG 2000 is based on. Okay, so now pursuing this viewpoint, how do we penalize now non-sparsity to reinforce our solution to be sparse, for instance, in wavelets? Well, we use the L1 norm. That's, a popular norm, which, and I guess, most of you have already seen this picture. Why is the L1 norm that beneficial? Well, because let's say if this is your solution space, you minimize the L2 norm, which is this ball, and the minimal solution in the L2 norm is this one here, but the minimal one in the L1 norm, which is this diamond shape, that's the ball for the L1 norm. This is this solution, so the L1 norm pushes the solutions towards the axis, and that's where the sparse solutions are. So this is a common strategy to do sparse regularization, where now you have a penalty term where you have here the inner products, for instance, wavelets, and then you apply the L1 norm, the little L1 norm to those. And so by doing this, then you penalize non-sparsity, so you enforce your solution to be sparse in wavelets. Okay. Good, but now the question is, how do you choose this system? Wavelets is one possibility. I would now like to introduce another system which also performs in various applications better than wavelets. So what is the viewpoint we take here? I think that's a common observation that images are governed by edge-like structures or curvilinear structures. So for instance, medical data, you see this here. The edge structures are those kind of which separate important regions. Also, the human visual system is very tuned towards recognizing edges in the first instance. So this is something which one would like to observe. And this is something which you would like to encode also in your system. So how do you do that? Well, first of all, we set up a model situation for what edge-like structures are. And then we design a system, generalization of wavelets to some extent, which behaves in some optimal way for these structures. So images which are governed by edge-like structures, there's a very popular model which looks like this, so-called cartoon-like functions. So how do they look like? These are functions which basically, look like this. So you have an outer area, you have an inner area, and then you have a distinctive discontinuity separating those structures. So you see this here. You have two smooth functions, and then one you restrict to an area. So, okay, so actually I even have a blackboard So it basically looks like this. So you have a function on the unit square, and then you have your area, which you call b. And so then you have inside a function which is f1 plus f2, and outside you have f1. Okay, so this is a model situation for images which are governed by curvilinear structures. So that's our model now. And now we would like to design a system which sparsifies these functions. So these will not be wavelets. Why not wavelets? Well, the problem with wavelets is that if you have, let's say, discontinuity curve, now wavelets are isotropic, so they are like a little ball. And if you approximate now a curve with wavelets, you need a lot. What would be much better is if you would have anisotropic shaped elements. And so this you see here. And now the idea is to design elements which have this shape. How do you do that? Well, I mean, you need, again, a scaling parameter. For wavelets in the 2D setting, you have 2 to j and 2 to j. But now you would like to scale in both directions in a different way. And so you scale here 2 to j and 2 to j half. This gives you elements which have a length of 2 to minus j half and a width of 2 to minus j. So they become arbitrarily needle-like at fine scales. You need another operation now to change the orientation of those. We use a shearing matrix because shearing keeps the digital grid invariant. So this gives you then faithful implementations in the end. And then taking these two operations and combining that with translation, which you see here, gives you what we call a shielded system. So you see, looks kind of complicated, but this is the tiling of the frequency domain which you get. So you have an inner part, which comes here from the low frequency part, and then you have different scales, same like wavelets. So this is related to j. But then you also have a directional decomposition, and this is related to the k. So you scale, you shear, and so you have different directions which you can distinguish. And so this is, for instance, one shearlet in spatial domain. Good. So, I mean, one can define a lot of things. What does it have to do now with this model situation of these curvilinear functions? Well, we can show, and there I don't want to go into the details, we can show that if you approximate a cartoon-like function with a shearlet expansion with n terms, that then the error which you make, the error rate, goes down as n to the minus 1, and this is the best you can do. So this shows that approximating a cartoon-like image with a shearlet expansion gives you, let's say, the best rate, and in that sense, a cartoon-like function is best sparsified by shearlets. So shearlets are, in that sense, an optimally sparsifying system for this model situation, whereas wavelets are not. So wavelets would have something like n to the minus 1/2 here. Yeah, so in that sense, I mean, shearlets are, from that viewpoint concerning also sparse regularization, a much better system than wavelets if you assume that your image is governed by curve structures, which is always the case. Okay, but then you can also take a different viewpoint now, and you can say, well, maybe I also would like to detect edges. I don't want to just sparsify it, but I would also like to have a system which detects edge structures. And this will be also important later on, and shearlets can serve that purpose as well. So this relates to this, what I said, this microlocal viewpoint. Yeah, so now we consider edge structures together with the direction, and we would like to get a notion for this and then see whether this can be also, let's say this problem can be also solved by shearlets. Yeah, so is this clear? So here, I mean, the first objective was to sparsify these functions. And the second is now we would like to detect, if we are given, let's say, an image like this, we would like to detect the edge, and you would like to also detect the direction of the edge. And so this will be later on important also for computed tomography, because there, I mean, in certain, let's say, instances, certain edges will be more easily be recognizable and reconstructible than others. So this leads to the definition of a wavefront set. So let me just explain it in a high-level viewpoint. I would like to show you the mathematical definition in a moment, but that's kind of complicated, so I think everything can be grasped here. Okay, so yeah. Okay, so what is a wavefront set? So let's assume, so this was actually gray, this area before, I don't know, it doesn't really show up here. So let's say, I mean, this is my discontinuity curve or my singularity curve. And the so-called wavefront set are the points on this curve, so the singularity points, together with their direction. So what is the direction of that point? Well, it's always the direction which is perpendicular to the tangent along this curve. So the wavefront set are the points on the singularity curve, and for each point, the direction in which basically the singularity propagates. So the wavefront set consists of points and directions. So how do you usually visualize this? There's a common way to do that in what's called phase space. So here, so this is a wavefront set. So here you have the spatial domain. Here you have the direction. And now you plot for every element of your wavefront set the position and the direction. So you see you have here, for instance, the position. And then the direction is something on this axis. So you go a bit up, for instance. So then here you have another point in the singularity curve. And it has this angle, and so on. So that's a common way to visualize the wavefront set. And later on, we'll basically see that, I mean, solving the limited angle computed tomography problem will be a problem of in-painting the wavefront set. So you can view this later on. You will see that as having a missing part in here. So this will be then the link. Okay. Is this so far clear? So then, I mean, you can make this all mathematical precise. Let me just show you the definition, but it is basically what I said there. So you can, I mean, there's a long definition. So this wavefront set consists of points and directions. So you can define what is a directed point, regular directed point. So basically what you do is, I mean, on your point, you put let's say, a function which localizes it there. Then you take the Fourier transform, and of the Fourier transform, you look in certain directions whether the Fourier transform has a decay, maybe rapid decay. If it has rapid decay or decay in a certain direction, then this is not an element of the wavefront set because it's smooth in that direction. So then the complement of these regular directed point, that will be the wavefront set. And so then, I mean, if we don't have the k here, it will be the complement of all points, which are k regular directed points for all k. But it's basically what I showed you on the previous slide. So let's maybe go back. It is exactly this. Points together with the direction. That's the wavefront set. Yes?
And but you told some part of this will be missing, right?
Sorry?
You told in this direction plot, some part of this will be missing later.
Oh yeah, later, I mean, when we talk about limited angle computed tomography, then it will be basically, you can phrase this as a problem that you have a missing part here to some extent, yeah. Okay, so and now, I mean, what does it have to do with Shearlets? Shearlets can identify the wavefront set. How can I do that? Well, now we again look at the Shearlet transform. You will recognize a slight difference to before, because now we have here continuous parameters, but again, it's the scale. This is the shearing parameter, and this is the translation parameter. And then what you can do is we look here at those coefficients. We let the scale go to 0. And we look at the decay of those coefficients. So we let the scale go to 0. If I have rapid decay, meaning it decays faster than any polynomial, then this position direction pair does not belong to the wavefront set. The wavefront set is then the complement of that. Yeah, but you see, I mean, by those properties of the Shearlet transform, you can exactly characterize the wavefront set. Yeah, so you can look at the decay properties if you let the scale go to 0, and those elements, again, these are position, direction pairs, these are then not in the wavefront set, so you have to take the complement. Yeah, so if you look at very fine scales, then basically the Shearlet coefficients can sense the wavefront set. So those which are large, basically, I mean, these are elements of the wavefront set. So that's the link. So basically, I mean, concerning Shearlets, there are a lot of properties which makes them quite nice for, in particular, imaging applications. So they are easily generated. You have sparse approximation of these cartoon-like functions. They resolve the wavefront set, which we saw before, so you can exactly detect directions and positions of singularities and direction. We can also have that in a compactly supported fashion, and there are actually faithful implementations. So there are that makes them quite effective, and you can use them, for instance, classically for in-painting, solving with sparse regularization. And if you're interested to try that out, we have a software package with various different languages. No matter what you speak, we hopefully have it here. So we have it in MATLAB, Julia, Python, and also TensorFlow. And there are also demos if you want to try that out. So that's all on that webpage. OK, so far so good. Good. So now let's come to medical imaging. So the problem I would like to consider is computed tomography. This we also saw already in some talks. It's based on the radon transform, which you see here. So we compute these line integrals, and we have the offset s, and then we have the angle phi. The problem becomes really hard if we are in the limited angle computed tomography setting, where we can only acquire data in a certain interval and not in the whole half circle. And so there are various examples where you have this problem, dental CT, breast tomosynthesis, and also electron tomography, which you see here. When you have a probe sitting here, and now if you turn this, then you cannot turn it 180 degrees, because otherwise the rays cannot get through. So you only have a certain angle, a range of angles where you can acquire your data. And the problem this causes, because now you have it's not low dose. It's very different from low dose, because now you have a huge chunk of missing data. And you can visually see what happens now if you just use a model-based approach, solving it with sparse regularization. If this is your original image, filtered back projection looks really terrible. So this is a 60-degree missing angle. But also, if you now use sparse regularization with Shearlet, so if you choose Shearlet system here, you still, have a huge blurry part, which is basically, with, let's say, these methods based on modeling, impossible to solve, because it's almost impossible to really, with a mathematical model how the human body looks from the inside. OK, so let's bring deep learning into the game. Now, deep learning is an exciting technique. From my perspective as a mathematician, it has also its drawbacks. And this was also already discussed in several talks, because right now, deep learning, Alchemy, there's a lot of mathematics missing. Just, as a side remark, I think maybe you're aware of this. There was an interesting incident in May 2018, where Ali Rahimi, in one of the big AI conferences, gave a plenary talk, and then he claimed deep learning is mainly Alchemy, machine learning algorithms in which computers learn through trial and error have become a form of alchemy. Researchers do not know why some algorithms work and others don't, nor do they have rigorous criteria for choosing one architecture over the other. And I think, in particular, in medical imaging, this is a tremendous problem. And in this whole area, I think what I like also as a guiding principle is what Stephen Hawking said. He said, the greatest enemy of knowledge is not ignorance, it is the illusion of knowledge. And I think in this area, we have to always ask ourselves, what do we actually know and what do we need to know, and do we know enough, let's say, to apply it in this sector? And so from my perspective, before we now return to computed tomography, what are important directions where also now a lot of theory is actually being developed are the area of expressivity, where people study, you have given architectures, how powerful are they, which are good architectures for specific problem setting. Then the learning algorithm itself, does it converge? Stochastic gradient descent, it's still not clear when it converges, how it performs in the over-parameterized regime. Generalization, why does it perform that well out of sample data? And you see, I mean, there are a lot of mathematical directions involved, which I also find quite exciting. And the last area, so these are basically also the components of a statistical learning problem. The last area I find quite interesting, which is this area of interpretability. And I think in this area of medical imaging, I would like to see more also in this direction. So this area studies the following problem. I have a trained neural network. I don't know how it was trained. I don't know which training data was used. I just have it. And now I would like to understand it. I would like to understand how it reaches decisions. I would like to understand how it maybe solves an inverse problem. So in that sense, people call it breaking open the black box. Because this situation we will always encounter, that we will always train neural networks where we don't have complete information on where they come from. And so let me just, maybe use, before we then continue, 2 slides to show you a bit what people have done in this direction. And then I think hopefully you see, there's a lot of, let's say, open room for also pursuing this research further. So what is this area of interpretability? In the easiest case, and this is basically how far people are right now, so if you have a network which classifies, let's say classifies digits, that's always the easiest, you would like to understand how important each pixel of your image is for the classification decision. Or, if you classify, let's say, cancer images, you would like to know how important each pixel is for this image being classified as coming from a patient with cancer. And so basically what people do is they put heat maps on this image, indicating that maybe the red points are important points, you see, because here there's a gap, and so this distinguishes this from an 8. And blue points are maybe points which speak against the decision of this being a 3. And if you now want to classify this as an 8, then these points are certainly very bad, because here, if it would be an 8, it would need to be closed. These points are quite good because they indicate maybe it's almost closed. And so there are, so this is how far people are. There are a lot of different approaches, more than which I could put on the slide. So there are gradient-based methods like sensitivity analysis, maybe the easiest one. You just look at the map and you look at the derivatives of this map. There are other methods where basically you take the decision and you back propagate it through the neural network to get to your input image and get the heat map on, and also other methods. So for instance, what we did, we defined, let's say, a more rigorous definition of relevance, meaning how important each pixel is using rate distortion theory, and formulated then this as an inverse problem. So if you're as an optimization problem, so if you're interested, I actually have a poster where everything is discussed in more detail. And so, the way you compare all those methods is typically, for instance, here you have classification of this digit 6. And so then you have a lot of different approaches. For instance, this is our approach, where you see, let's say, for instance, here you see this is an important area, distinguishing this from an 8. Also, this area is important, which also somehow supports that this becomes a 6. And then you have plots where you can fairly compare those, maybe comparing the number of important pixels versus the error in classification. But in general, I think, this is, as I said, an area where people are just at the beginning, in a sense. So here you could also say, why do you consider certain pixels? Maybe also clusters of pixels are important. Not every single pixel is maybe important for itself, and so on. So I think in this area we will see much more in the future. Okay, so now let's come back to deep learning and inverse problems.
So
yes?
I have a question. So there information content for a certain pixel. Is there research that does this and generate these heat maps?
How do you generate those?
Yeah.
Yeah, so there are a lot of different approaches here. Yeah, so for instance, here these backpropagation methods do the following. You have a, I don't know, you have some your input image here, and then you have your decision. Yeah, and so what those do is, I mean, you have a decision, and then you backpropagate the decision basically through the network in some sense. You always branch out, and this gives you then for each pixel a certain value. Yeah, so that's in a way these methods of backpropagation. They backpropagate the decision and giving a, let's say, an importance value here for each. I mean, it doesn't really give a definition of what relevance is. So what we basically did was we said, let's say the pixels which contain the key information. So if you distort the other pixels, then the decision doesn't change much. Yeah, so in that sense, I mean, this is, let's say, where our approach is based on. And so there we have a rigorous definition of relevance. But I mean, in general, there are a lot of different approaches. Yes?
So how do we validate this automatically? Like, let's say we assume we generate all these heat maps and these sort of salience methods.
You mean compare them, or do you mean it's validate?
Evaluate. Let's say there is something as a baseline, and how do we evaluate? Maybe, yeah, of course, we can eyeball them and just
so
means that it's okay.
So
But
how you let's say, compare them could be something in a plot like this. So here you have the number of important pixels, and then maybe you rank them, and you start distorting the other ones, the less important ones, and at some point the decision will flip.
yeah.
And what you would like is that it flips at a very large point. Yeah? And so this is indicated then by those lines.
Okay.
Yeah? So this is the way to compare it. Validating, I mean, it depends on what relevance actually is.
Yeah.
So, yeah.
Not very well clear.
I mean, yeah. I mean, we have, I think, a rigorous definition. I mean, others backpropagate, but I mean, there's no definition of what relevance is. I mean, it is what they get out.
Yeah.
Yeah. So therefore, I say, I mean, there's a lot of room for making it more rigorous, proving results, and so on.
Something LRP system.
Sorry?
LRP.
LRP. Yeah, LRP. So this is what I have here, LRP. Yeah. Okay. Okay, good. So deep learning and inverse problems, we saw already several approaches, so maybe I can go quickly through those. There is first using model-based inversion, and then followed by neural network for removing artifacts. You also already saw plug and play with CNN denoising. So you have trained neural networks, which you then insert in certain parts of your recovery algorithm, learn iterative schemes where you, for instance, learn proximal steps, learn proximal operators. There's also this learn primal dual here, for instance, from Jonas Adler and Ozan Öktem. You can have priors based on generative models and so on. So there are a lot of different ways how to combine that. What I would like to pursue now is, as I said, I would like to use model-based approaches as far as possible, and then use deep learning only where you cannot get any further. And the guiding principle which I would like to pursue is that edges are the key features of the image. I would like to pay particular attention to how the edges, let's say, propagate or are recovered, because then, I mean, for instance, if we could recover the wavefront set in the first instance, we could use it as a prior. It can reveal which parts of the image are missing. And how I would like to go about this is, I would like to use that the Shearlet transform is in some sense able to sense the wavefront set. So you will see how this appears. So let's start with the first of the approaches, learning the invisible. This is joined with my PhD student, Maximilian Merz, then 2 colleagues from the Fraunhofer Heinrich Hertz Institute, and 3 colleagues from the University of Helsinki. Okay, so this is about limited angle computed tomography, and we got inspired by the very nice work by Ye, where he studied also the limited angle computed tomography problem in a way by first computing a wave-fit transform and then using a convolutional neural network here, a unit on the wave-fit transform. But from our perspective, we didn't want to process the entire image with a neural network. We only wanted to learn what you cannot learn otherwise, because from our perspective, I mean, it is then not really clear which features are modified. We only wanted to modify those features with a neural network which you don't have any chance of recovering by a model-based approach. Okay, so let's take a look at what happens actually in this problem. Now, let's assume I only know an angle from -15 to 15 degrees. That's the only data I have, and then I'll recover. So then you recover this, which looks horrible. Now, if you increase the angle, you see it's getting better and better. What you also observe is that certain parts of the singularity structures are already visible at an early stage. So you see that here at a very early stage, you know that there is a singularity curve, and you know there are its direction. So certain boundaries or features are at a very early stage already visible. But the others are then blurred. And so this you can make mathematically precise. So there's a result, an old result from '93 in this area. I mean, this is an ancient result where Quinto could detect exactly which part, how elements of the wavefront set of F are related to the wavefront set of the Radon transform of F. Basically, I mean, intuitively, maybe if we look at this picture, it's becoming intuitively also clear. If you sample along lines in this direction, then certainly these singularities you will not detect because they are just smeared out. But here you will at a very early stage already see that there is a singularity, and also you will know its direction. It's basically perpendicular to the direction along which you sample. And this we would like to explore. So you see, I mean, in that sense, remember wavefront set, what I said before, singularities together with their direction. So at a very early stage, you know this are singularities, and you know the direction of those. Here, you don't know anything. So basically, the task you have is now, you know parts of the wavefront set, and basically you would like to inpaint the wavefront set. You would like to detect the other singularities and their direction. And we try to do that with a prior, to handcraft a prior, but that, I mean, it's just too complicated. So what is the idea now? First of all, I mean, the Shearlet transform will be one ingredient, because this, as we already discussed, is able to sense the wavefront set at fine scales. And it is also able to distinguish which parts I know and which parts I don't know. Because remember, this was the tiling of the frequency domain by Shearlets. And now if you look at the part which you know and which you don't know, you can also visualize this in the frequency domain. So you have a part which you know and a part which you don't know. So the Shearlets can, in a sense what you know and what is unknown. And then the basic strategy is we first just do, and I will show you the details in a moment, we first just do sparse regularization. We recover. And then we will get this blurry part in a certain area. And then we would like to use deep learning, but only to recover the blurry part. And how do we, let's say, sense which parts I did not recover? Well, I compute another Shearlet transform. And this Shearlet transform will tell me which parts of the wavefront set I already recovered and which not. Okay, so that's the basic idea. So let's see how it looks in detail. So first, we solve a classical sparse regularization problem. So you see, I mean, that's what we always do. Here we have an L1 term. Well, it's weighted because here I have a multi-scale system, so I weight the different scales. But basically, I have an L1 term here, and these are Shearlet coefficients. So inner products of F with Shearlet elements. This is very classical. So then I recover an image which is blurry in those areas. Now, I would like to access the wavefront set of this. And so what I do for this, from the solution F star, I compute another Shearlet transform. I again compute a Shearlet transform, and what I now observe is that some of those elements are close to 0, and the others are reliable and almost perfect. So that way I can distinguish between that part of the image which I can already recover precisely, and the other part where I don't have enough information to do that. So let me heuristically argue or empirically show you that this is actually the case. And then we continue. So let's say this is my ground truth. And I do limited angle computed tomography. This is my filtered back projection recovery. Now, if I use sparse regularization with Shearlets, I get this. So I still have this blurry part here. And now what I do is I take from the F star certain Shearlet coefficients, and I augment this with the other Shearlet coefficients from the ground truth. And then I go back. And so what you see is, by doing that, so by augmenting a certain part, I get actually a perfect recovery. So that means these Shearlet coefficients are already perfect. And I just need to, let's say, replace certain of the Shearlet coefficients, namely those with the indexing set, which we call invisible. So certain parts are perfect, the others I need to modify. And so this is what we see here. So certain Shearlet coefficients of my solution, these I need to modify, the others I don't touch. So that's the main part here. I only touch what I cannot recover otherwise. Okay, and so how do I recover those? Well, there I now use a neural network. So now I take the visible ones, so I take those which are reliable, and from those I recover those which are invisible. So and I train it with the ground truth. And then I augment the ones which are reliable and nearly perfect with what my neural network gives me, and then I go back. But you see, I very precisely, surgically, somehow only replace those parts which were not perfectly recovered. And so I take, as usual, a unit for training this. The advantage from our perspective is that you can actually exactly tell what the convolutional neural network does. It does 3D in-painting on the wavefront set, and it only learns what you cannot do otherwise. And so we will see the performance is actually quite good. You get also not that much blurring. Certainly, the speed is dominated by, since we, at the first step, we do an L1 recovery. Okay, so let's look at some examples. We had data from a Mayo Clinic. So here, in the first instance, we have a 60-degree missing angle. So we take 9 patients for training, 1 for testing. We pre-train our neural network with artificial ellipses, and then we fine-train it with these patients. And in a second step, I will show you also results of the neural network on a very different data set, which it has never seen before. So this is, in some sense, to test generalization. Okay, so that's the ground truth. That's filtered back projection, recovery. That's the relative error. That's a different measure, which is, in some sense, an improved measure, better than the self-similarity index. So that's very much adapted to the human visual system. Okay, that's filtered back projection. That's TV. This is sparse regularization with Shearlets. That's our F star. So it looks here. So you see, here, a lot of distortions which were not recovered perfectly. Then, this is the approach by our colleagues from South Korea, where they use a Wavefront transform and then a neural network on the entire image. So you see this is better, certainly much better than this. And now we use this combination of using a model-based approach and only a neural network for those coefficients which you cannot do otherwise, and this is what you get then. And if you like metrics, then you can compare all different approaches with relative error, PSNR, self-similarity index, and HARP psi, which is actually a quality measure which we introduced, which has which you can compute very efficiently, and which also has much higher correlations to the human visual system. And if you're interested in this algorithm, you can actually just download it from our webpage. But you see, I mean, all those metrics, our algorithm perform the best. And so now, let's look at different data set which the network has never seen before. So that's a Lotus root sliced and puts some metal stuff put in. That's the filtered back projection recovery. So that's now only 30 degrees. So therefore, it looks a bit better than before. That's TV. This is sparse regularization by Shearlets. Now this is using neural network on the entire image with wavelets, and then this is what we got. Okay. So that's the first, and now, I mean, the last maybe 5 minutes, let me show you also a second type of approach, which is to some extent also then, I mean, we are pursuing this a bit further. So this is now joint work with another of my PhD students, Hector Andrade Lorca, with Ozan from the KTH, and with a former PhD student and postdoc of mine who is now a professor in Vienna. So there, the philosophy is a bit different. We want to use a wavefront set as a prior. So now, the idea of the course of action is we have a sinogram from which we want to recover. And let's assume I know the wavefront set of this. Then I can bring the wavefront set via a certain relation to the reconstructed domain. So I know from the reconstructed image already the wavefront set. And I can use this as a prior. Yeah, so there's what's called a canonical relation. It relates the wavefront set of the radon transform to the wavefront set of F. And so the idea is to first extract the wavefront set from a sinogram, then bring this in a way to the domain of my reconstructed image, and then use this as a prior for my reconstruction. Now, is this clear? Okay. Now, how do you do that? How do you recover a wavefront set? So there are certainly all these edge detection algorithms, but we wanted to pursue again this strategy, driving a model-based approach as far as possible, and then using a neural network for doing the rest. And the idea which we do here is we first compute a Shearlet transform of the image, because remember, a Shearlet transform can already sense the wavefront set. So we have already good data representation. We then take patches of the Shearlet coefficients, and then we apply a neural network to detect from those Shearlet coefficients then the direction. So basically, the neural network does the fine-tuning to detect then the direction, and we have 180 directions which the network can choose. Yeah, so this is a neural network. We have here convnets, and then we use a fully connected network in the last layer. And the training, I mean, also goes steps by steps. We first train on random sums of ellipses, parallelograms, and then we train it on real data. Okay, good. So let me show you some numerical results. So this is kind of artificial data. So you have here a combination of ellipses and rectangles. So there you would like to detect the wavefront set. How do you visualize this? Well, I mean, you have the singularities here, but now we color code the singularities depending on the direction. So there are 90 degrees, for instance, this kind of bluish purplish stuff. Yeah, so I mean, depending on the color here, this indicates which direction the edge has. And so a human would do this. So for this, a human, I mean, would do actually a quite good job. There are different approaches which have also the same task or the same goal to recover the wavefront set. And so this is our approach. So you see, I mean, it's actually much better than this approach, also a bit better than this approach. It becomes a bit more difficult if you take a blurry image here, because there, I mean, it seems very hidden. A human is, again, I mean, doing a great job, because there, I mean, you can still see the edges, but I mean, the other algorithms completely fail, whereas ours still is able to recover the edges very precisely and also the direction of the edges. And also, again, I mean, if you like metrics, there's a so-called MF score, which basically studies, so P is the precision with which you recover, and R is the so-called recall. The larger, the better. So you see, if we now compare our algorithm with other algorithms, it performs, in some sense, the best. Now, if you have more realistic data, you see, I mean, a human does actually a terrible job to detect directions or to detect edges and directions. There are other algorithms, but again, I mean, our algorithm performs much better. You see, I mean, you see all these different fine structures here, also here on the boat, and all of those are recovered together with direction in a very precise manner. And so now, again, if you compare these metrics, you see, I mean, there's a huge difference between what people have done before and now with these, let's say, combination of a model-based approach, namely Shearlets, with deep learning. So there, I mean, you can very precisely recover singularities and their direction. Good, so this was this idea, and let me just show you 2 examples in the end, which now relates, and we are also pursuing this now further. So if you now have a sinogram, if you have a phantom, you compute the wavefront set using our algorithm. This is a sinogram, and then you can bring this by the canonical relation in here. Then you see that you get actually a quite good approximation of the wavefront set of the sinogram, but the more interesting direction is backwards. You have a sinogram, for instance, a Lotus sinogram, where you have only each 6th angle. You compute the wavefront set with our algorithm, then you use the inverse canonical relation to bring this back, and this is what you get. So there you already have a very good approximation of the wavefront set of your recovered image. And now you can use this as a prior for recovering the image. So you see, if you compare this now with, if you just recover without taking care of the edges, then you see you do a much better job using these canonical relations. OK, since I'm already over time, let me finalize. So what I showed you was that on the model-based side, one canonical approach is sparse regularization. Shearlets is one way to go, assuming that images are governed by edge-like structures, which is, I mean, a usual assumption and typically the case. On the other hand, we have deep learning, where we still are lacking a bit on the theory, but for inverse problems, it's actually an amazing technique. What I would like to pursue and propose for my talk is to drive model-based approaches as far as possible using deep learning for the rest. I showed you 2 approaches in this direction. Learning the invisible, where we first accessed what you can recover using sparse regularization of Shearlets, only learning the invisible part precisely. The other strategy was to use the wavefront set then also as a prior for reconstruction, and for this, as a first step, I showed you an extractor for extracting the wavefront sets, again using Shearlets in combination with a deep neural network, and then using the canonical relation to use it, to apply it as a prior. OK, that's it. Thank you very much.